Hello. Okay, so we're going to discuss matrices, arrays, and vectors. These terms are used interchangeably, but each one has a meaning, and Matlab is all about them, about matrices, arrays, and vectors. So let's just go through the definitions. First is what is a matrix, and a matrix is a collection of numbers. As you can see, the matrix A here, it has 3 rows and 3 columns. And if I want to input this matrix into Matlab, all what I have to do is separate the elements in the row by a space, as you have here, and separate the rows by a semicolon. So this is to separate the rows, and the elements are separated by the space. It doesn't matter how many spaces you have. You can have 2 or 3, but it doesn't matter. As long as you have a semicolon in between, then the elements are entered, and you can see different forms here with many different spaces, and the colon, semicolon is in between. So that's the first step for us, is to how to introduce the matrix, and then we want to see how we would allocate the size of the matrix, because the matrix has m rows and n columns. So usually in the beginning of the program, we try to allocate the size so we don't get confused later on and not know what the size is. So pre-allocate with a special function that produces zeros in every element, and here it is. So if you say C equals zeros of 5, this gives you a square matrix that has 5 rows and 5 columns, which is equivalent to zeros of 5 comma 5. Also, if you write zeros of 5 comma 8, it gives you 5 rows and 8 columns. And you can also have a matrix A, so you can use this function called size of A. This function size of A gives you the m and n of the, which is kind of a vector, gives you a vector, and the vector has 2 numbers in it, m and n, and those can be used again here to generate zeros in another matrix C. So let's try to do something here. Here's the Matlab, and we're gonna try to demonstrate those here with you, and if we will see that, let me try to bring it up a little bit so you can see. If I have a matrix A, and then I say that A is zeros of 5, then it will give me 5 zeros by 5 zeros. But if I say A is equal to zeros of 5 comma 1, this should give me 5 rows and 1 column, and that is basically a column vector, and that's why A is a column vector. So if I say A of 2, that is the second element in the column vector, which is 0. So this is a specific element. And if I want to get the size of this matrix, so I say size of A, let's see what's going to happen here is that you see that I have 2 numbers. It's a 5 by 1 because we have 5 rows and 1 column, which is the matrix is A here. We're not referring to the previous one. The previous one now has been replaced with a new one, and the new one is just what we call a column vector. So this is a column vector. So if I say, let's say A, and give it the transpose of A with the apostrophe, that should give me a row. So it should be a row vector, and the row vector is 0, 0, 0, like you can see here. One word that I would like to say is about the apostrophe. Essentially, we should have a dot before the apostrophe to produce the row vector. So you can, what I'm going to do now is that the last value of A is, we have, this is called the conjugate. We can get the conjugate by this operation with a dot and an apostrophe. But if all the numbers are real, then the conjugate is the same with or without the dot before it. So in other words, what we learned so far is that we have a matrix A. If I just take the apostrophe, this will switch it. It will be rotated 90 degrees, and it gives me the conjugate matrix. And if I just have A dot prime, this gives me, actually this will be conjugate for real numbers in the matrix. The last operation with a dot is the conjugate if we have complex numbers. So if we have real numbers, then it doesn't matter whether we have a dot or the apostrophe. They'll just produce the same exact result in taking the matrix operation. So there's a number of commands here. These are functions, basically. If we have zeros of n, it generates a square matrix. Mn generates m times n. Zeros of size A generates a zero matrix with the same size as the matrix A. We also have other matrices that are special. I can use, instead of zeros, if I say ones, then it gives me 1 everywhere in the matrix. If I say I, it gives me ones on the diagonal, which is identity matrix, we call it. These are other matrices, rand and so forth, for random numbers, so let's ignore those ones here for simplicity. And just concentrate on the idea of size. So the size obviously gives me these two numbers, m and n. If I have a vector, whether it's row or column, instead of using the word size or the function size, we use the function length. So this is for a vector. So we say length of x instead of size of A. A is for a matrix. This would be for a vector. An equivalent one is a function called number of elements, NUMEL, and it gives also the total number of elements in a vector or matrix. So with that, we have an idea about the matrices here, and as I defined it, the transpose with the dot before it. This is the formal definition of a transpose, which is basically taking the matrix and rotating it 90 degrees and without changing anything. But if we put a apostrophe only, it gives us what's called the conjugate transpose. In other words, it will take the matrix, rotates it 90 degrees, and it will change the sign of the complex numbers in there. So if I have a complex number that has real and imaginary, then it will change the number, the sign of the imaginary. So if we have all real, it means that either conjugate transpose is the same as the regular transpose of the matrix. Moving on with the matrices, we can extract data from matrices by typing a number of commands for different functions, and those are the ones that you see here. So I will go through the commands that can extract some data from the matrices. First is that if I use the command A of I and j, like I did before, let's say A of 2, 1, it will extract the element that resides in row 2 and column 1. Instead of I, if I put colon, then it will extract the entire column j with all of its rows. So when we have the colon, we mean implicitly all values in that row. So it's all rows, and then column J. Here is row I, column, and all columns. So this means that this is actually is a way to access or to make a column vector, and this is a way to make a row vector. Again, if I put a colon colon, it means that I want everything, so that gives me the entire matrix here. One idea, let's skip that one, a and then colon, this would give me a vector instead of now this is a matrix. This gives me all the elements organized in a matrix. This will create a vector that is made up of all the columns of the matrix A. So it will take each column, the first one, and then take the second one, put it underneath, the third one underneath, and so on, and it gives me basically a whole vector. These are a number of commands that I'm going to leave for you to review in the lectures that pertain to extracting a diagonal from the matrix, the diagonal exactly in the center, which is k equals 0. Diagonal is offset by a value k, so it's above the center by 1 or 2 or 3, so k can be like this. And then in matrix algebra, we sometimes solve linear equations with triangular parts of the matrix, so we can extract the upper triangle that comes from the matrix, or the lower triangle, so upper or lower. These are special functions that sometimes we use to solve linear algebra problems. Now I come to an important part of the matrix idea, is that how do we solve systems of linear equations. So in systems of linear equations, we write them usually as a matrix A times a vector x equals a vector b. And we learned Gaussian elimination, for example, as a method to solve it, or matrix inversion. So Matlab offers great advantage in this case by just using the simple command that we will see here. So if we look at a problem, we have a matrix A times a vector x equals a vector b, and I want to solve this problem for x. So this is b is known and a is known, so these are known. In Matlab, what we could do is just simply take a to the other side and divide by it, and the way that we divide it is from the right to the left. So the idea is that we can write x equals b divided by a, and that would be the solution of the linear system. So when you write x equals b divided by a, you get the solution directly, and this is equivalent to another command called inverse of a times b, which is the inversion of a. You know, if you take a to the other side, you invert it. But this is slower, especially if we have large matrices, and this is done by Gaussian elimination, which is a fast method for non-singular matrices. So that is a very nice feature. We could extend the same idea, is that if we write x equals b, where b now is made up of a bunch of vectors put together, like b1, b2, b3, etc., then you can solve x that you have here as equal to b divided by a again. So this solution gives you now a matrix for the result of many systems, like you have system 1, system 2, system 3. So if you vary some variable and you get different forcing functions on this side here, you can arrange them all in a matrix, and then if this matrix A is the same, which we can call a stiffness matrix in this case, then the solution is also obtained by just one simple command. Moving on to matrices, the dot product is, we have two different kinds of products, and the product is that suppose that I have a row vector and a column vector, like this is a column, this is a row, and I'm multiplying, this is, let's say, one this is 5 rows by 1 column, and this is 1 row by 5 columns. So when I multiply this vector by this vector, then I multiply 5 times 1. Let me just write it here so clearly. In this case, I multiply 5 by 1 times 1 by 5. So the 1 in between is essentially consumed, and the result should be a 5 by 5 matrix. So this is the way that we multiply matrices in general. If we reverse these two and write this first before that, then let's say I have a row vector times a column vector. So this one is 1 by 5, and this one is 5 by 1. Then the result is 1 by 5 times 5 by 1. Then the 5 is consumed, and the result should be 1 by 1, which is a scalar. Okay, so these are two different ways of multiplying two vectors. Sorry, two different ways of multiplying two vectors. Either that you get a matrix or you get a scalar, which is kind of interesting. So if I have two vectors and I multiply them together and I get a scalar, which is one number, then I say that I term this inner product. So inner, like it's just kind of contraction. If I get a matrix instead of a number, then I say that this is an outer product. So I can get basically expand the two vectors and become a matrix. So as I remember here, two different ways of multiplication. We have to be very careful when we do the multiplication with Matlab. So for example, if I have now two vectors, one is A transpose and B. This will be the A transpose, and this is your B. And well, actually, it should be A transpose would be a row vector like this, and then the B is a column vector. So one row, one row times 5 columns, and then here is 5 columns times 1 row. So this is A, and this is B transpose. If I multiply these two together, I would write A star B transpose, or if I reverse them, then I can write A transpose star B, and that should produce the inner product of the two vectors. So there's a few ways to do that, and I would like to kind of try them out with you on here on the screen, as long as we can play with these multiplication rules here. So let's say I create a vector x, and x is some numbers 1, 2, 3, and then that's a row vector, and then I create a vector y, and y is 4, 5, 6, and then I'm gonna take the transpose of that vector. That's gonna should give me, flip it to 90 degrees. It should give me 4, 5, 6. And if I want to have z is equal to a x, which is 1 by 3, and then I multiply this directly by y, which is 3 by 1, then the result is that the 3 it disappeared, and I get actually a scalar, which is one number. So I get here basically a dot product, right? Now let's say that if I have, instead of 1 by 3 and 3 by 1, I want to do a 3 by 1 times 1 by 3. So 3 by 1 would be y. So let's say z equals now y. So y is 3 by 1. And I multiply this by x, which is 1 by 3, like that. Then the result is a matrix. Wonderful. So that would be the outer product. So with that, we see that we have a number of possibilities to generate these products of matrices, and we just have to be careful applying the simple rule that I mentioned in having these products. One of the big advantages of matrices is that they organize everything in columns or in rows, if you think about it. And there are a number of functions that we can use in Matlab to extract important information. For example, if I'm interested in the maximum of numbers in one column, I can find that by just one function called max. And the same for minimum. And then if you just extend this to different statistical methods, then you can basically get the mean value, which is average. You can get the standard deviation, which is kind of the spread around the average of a bunch of numbers organized in one column or one row. Or you can get the sum of all of the numbers, or you can get the product, and you can use, or you can get the difference between them. You can use all of that to your advantage to do very elegant programming. So let's say that we can review them first and see how they apply. So max of x, it gives you the maximum element of a real vector. And if you enclose the result like that, for instance, if you say, let's say if I have a equals max of x, this gives me one number, which is the value of the maximum, and stores it in a, right? But if instead of a, I can write here a and then comma I, and then I write max like this one here, it will give me actually the value of the maximum and where it is. I is the location of that maximum. So that can give me where it is actually in the column vector that I have, whether it's a column or a row vector, doesn't matter. I can extend this to a matrix, and if I have a matrix, it applies the maximum function to each column independently and produces a row vector. So the row vector now will have all of the numbers similar to the maximum. We have here one number only for x, it gives you one value. But if you have a matrix, then the matrix would be organized. You have a bunch of values here, a bunch of values here, a bunch of values here. So it will pick the maximum here, picks the maximum here, pick the maximum here, and then it will organize it for you. This will be the first location, this will be the second, this will be the third, and so on. So that value, this will be your vector that contains the maximum. It's a row vector that contains the maximum values everywhere. You can apply the same thing for minimum, sorry. So this is minimum, this is incorrect. So this is the minimum. The mean value, same idea. The norm is the square root of like the length of the vector. So we take a1 squared plus a2 squared plus a3 squared and so on. It's like taking the length of a vector and taking the square root. This would be some number, and that's called the norm of the vector. And that could be useful sometimes to measure the length of the vector itself. And we can also continue to use sorting, products, standard deviation, sum, and difference. And the difference in particular is important because when you have diff command, this is not a command, it's a function, diff of x, it produces a vector y, and y is the successive differences between elements of x. So let's say if x is equal to 3 and then 2 and 5, then y will be the difference between these two. It will be minus 1. The difference between these two will be 3. And minus 1, 3, the vector y is 1 less than the vector x because it's a difference. So sometimes we do use the diff function to our advantage in actually doing differential equation or differential of a function. Also we use it in integration. So let me give you like an example. I prepared a little script here, and the script is actually let's see, it disappeared here. Here is the script. So the script is shown where we have in fact the elements of the script showing the small function. Let me just kind of put myself, and it shows here that I have a vector x that represents a collection of numbers for the temperature measured for copper. So the 70, 80, 90, 100, and so forth. So this is x. And then I have y would be corresponding conductivity, 171, 203, 229, and so on. So I have two vectors. These are row vectors. Each one is 19 elements long. So if I take del x equals diff of x, that gives me another vector that is only 18 elements long, and it will be the differences between the elements of vector x. And if I also say del y, it will be diff y, that gives me the differences in the elements in the vector y. Now if you look at the next line, is dx by dy equals diff x dot backslash diff y. This means that I'm dividing every element, every difference in x by every difference in y. That gives me dx by dy. So I'm differentiating x with respect to y. And I can do also the sum of y and multiply by 10. 10 is the distance between each element here to give an integral. I can produce z equals zeros of length x minus 1, because that is the z vector. I want it to be 1 less than the x vector. And then I can do a for loop on the vector y, and the for loop is going from I to length of y minus 1, and I create the vector z by taking the average between two consecutive y points and then store that in z, and therefore if I multiply z times del x, and that should give me the integration of the function that I'm requiring in here. So these are all